In late 2024, astronomers spotted something extraordinary. About 1 billion light-years from Earth, a dying star had detonated, but this was no ordinary supernova. It blazed roughly 30 times brighter than a typical stellar explosion. That extreme luminosity placed it among the rarest cosmic events ever witnessed, earning the classification of superluminous supernova. Only about 300 of these extraordinary blasts have ever been cataloged, making each one precious to science. The team designated this event SN 2024 AFAV. Yet the real puzzle was not its brightness alone. As researchers tracked the fading glow night after night, the light refused to follow the smooth, predictable decline that physics demands. Instead, the brightness wobbled, rising and falling in rhythmic pulses that grew faster and faster. Over the months that followed, no stellar explosion in recorded history had ever displayed such behavior. The team coined a striking name for this strange signal, a chirp. They borrowed the word from gravitational wave astronomy, where colliding black holes generate an accelerating hum before they merge. Something hidden inside that distant fireball was pulsing like a cosmic heartbeat, and the beat was speeding up. Observatories on every continent swung their instruments toward the same fading patch of sky. The race to decode the chirp had begun. To understand why this chirp mattered, consider the mystery that has haunted astrophysics for 2 decades. Superluminous supernovae were first recognized in the early 2000s, and from the start, they defied explanation. A normal supernova occurs when a massive star exhausts its nuclear fuel. Its iron core collapses and the outer layers blast outward in a blinding flash. The glow then fades steadily over weeks. Superluminous events, however, shine 10 to 100 times brighter and stay luminous, far longer than any standard model predicts. Something extra must be feeding energy into the expanding debris. 2 competing theories emerged. The first suggested that the supernova shockwave crashes into dense shells of gas, previously ejected by the star, converting kinetic energy into additional light. The second, proposed in 2010 by theoretical astrophysicist Dan Kaysen at UC Berkeley, offered a more radical idea. Kaysen argued that when an extremely massive star collapses, it can forge a magnetar instead of a black hole. This ultra-dense neutron star, barely 16 kilometers across, spins more than 1,000 times every second. Its magnetic field dwarfs anything else in the known universe. As the magnetar spins down, it pumps enormous energy into the surrounding debris, keeping the supernova bright for months. The idea was elegant, but for 16 years it lacked direct proof. The proof arrived on March 11, 2026, when Vera and his colleagues published their findings in the journal Nature. Their paper centered on SN 2024 AFAV, the chirping superluminous supernova, tracked by 27 telescopes belonging to the Las Cumbres Observatory, a global network spanning every inhabited continent. For more than 200 days, these instruments captured the supernova's light curve with extraordinary precision. After the initial brightness peak, roughly 50 days into the event, the glow did not simply fade. It produced 4 distinct bumps, each one arriving sooner than the last, tracing a pattern that looked unmistakably like a chirp waveform. Vera built a computer model to recreate the light curve from the inside out. The simulation required a central engine, a newborn magnetar, whose magnetic field measured roughly 300 trillion times the strength of Earth's own field. At that intensity, the magnetar's influence extends well beyond its tiny surface. Material from the exploded star fell back toward the magnetar and formed a swirling accretion disk. Because the disk was not perfectly aligned with the magnetar's spin axis, it sat at a tilt. Here is where Einstein entered the picture. The spinning magnetar dragged the fabric of spacetime around itself, a phenomenon called Lense Thirring precession, forcing the tilted disk to wobble like a cosmic spinning top. That wobbling disk transformed the magnetar into a cosmic lighthouse. As the disk precessed, it periodically blocked and reflected the magnetar's intense radiation, creating a rhythmic flicker visible from 1 billion light-years away. But the truly remarkable feature was the acceleration. As the accretion disk spiraled inward, closer and closer to the magnetar, the Lense Thirring effect grew stronger. The wobble quickened, and so did the flicker. The first oscillation cycle lasted roughly 32 days. The next shortened to about 24. Then the gap shrank further, By the final observed bump, the cycle had compressed dramatically, producing the characteristic chirp, a frequency that sweeps upward, much like the signal from two black holes about to collide. Vera and his collaborators tested every alternative they could imagine. Could ordinary Newtonian gravity explain the timing? It could not. Could the magnetar's own magnetic field drive the precession at the observed rate? The numbers failed to match. Only when the team applied Einstein's equations of general relativity specifically. The frame-dragging component did the predicted periods align perfectly. With the observed data, it was the first time in the history of supernova science that general relativity had been required to explain the mechanics of an exploding star. The finding carried an additional reward from the chirp pattern the team extracted, the magnetar's spin period, pinning it at just over 4 milliseconds per rotation. With the magnetar confirmed, a deeper question surfaced. What happens next? A newborn magnetar is among the most volatile objects in the cosmos. Its staggeringly powerful magnetic field places enormous stress on the star's crystalline crust. Over time, that stress can fracture the surface, unleashing bursts of energy so intense they outshine entire galaxies for a fraction of a second. Some scientists believe these outbursts are the source of fast radio bursts, mysterious millisecond flashes of radio energy that have baffled astronomers for years. If the magnetar inside SN 2024 A5 eventually produces such bursts, it would forge a direct link between superluminous supernovae and one of modern astronomy's most tantalizing puzzles. But that is only one possible fate. The magnetar's spin will gradually slow as it radiates energy, and its magnetic field will weaken over thousands of years. It may settle into a quieter existence as an ordinary pulsar, beaming steady radio pulses like a celestial metronome. Alternatively, if enough material continues falling back onto the magnetar, the added mass could push it past a critical threshold. At that tipping point, the neutron star would collapse entirely, vanishing behind an event horizon to become a black hole. 3 futures branch from one stellar death radio beacon, quiet pulsar or black hole, and nobody yet knows which path awaits. The chirp is more than a curiosity. It may become one of astronomy's most powerful new tools. Until now, confirming whether a magnetar powered a superluminous, supernova required indirect reasoning and educated guesswork. The chirp changes that entirely. If future superluminous, supernova also display accelerating brightness oscillations. Astronomers can decode each chirp to measure the hidden magnetar's spin rate, magnetic field strength, and accretion geometry from across the observable universe. The timing could not be better. The Vera Rubin Observatory in Chile is preparing to conduct the most ambitious sky survey ever attempted. Every few nights, its camera will photograph the entire visible sky, generating 10 terabytes of data each session. Current estimates suggest the survey will discover thousands of new, superluminous supernovae over the coming decade, a staggering leap from the roughly 300 known today. Among those thousands, many may chirp. Each chirp will offer an independent measurement of how general relativity operates, under the most extreme conditions nature can produce. Other facilities stand ready to join the effort. Space-based observatories can extend coverage into the infrared, while future gravitational wave detectors may directly sense the spacetime ripples these magnetars create. A single chirping supernova rewrote a chapter of astrophysics. An entire chorus of them could rewrite the book. When Joseph Vera first noticed the rhythmic flicker in SN 2024 AFAV, he described it as having a conversation with the universe. For over 100 years, Einstein's general theory of relativity has been tested in settings from the orbit of Mercury to colliding black holes. Yet no one had ever seen its fingerprints inside a supernova until a dying star, a billion light years away, sang a song that only relativity could explain. The chirp was more than a signal. It was an answer to a question astrophysicists had asked for 2 decades. What powers the brightest explosions in the cosmos? Now we know a magnetar, forged in the final moments of a massive star's life, spinning at unimaginable speed, dragging the fabric of space and time around it. The death of that star was not an ending, but a beginning. A new object was born, a new signal was discovered, and a new way of studying the universe emerged. Beyond our galaxy, another massive star will one day exhaust its fuel and collapse. It may produce its own chirp, a fresh cosmic message waiting to be decoded. All we have to do is keep listening. The universe, it turns out, has been singing all along.